Everything you touch, everything you see, and everything that has ever existed owes its weight to a secret most people never think about, not gravity, not energy, something far more hidden, something so small it cannot be seen, yet so powerful it decides whether the universe can even exist at all. Deep beneath the surface of reality, beyond atoms and particles, there is an invisible rule that shapes everything, and for decades scientists were not sure it was real. They believed in it, they wrote equations about it, but they could not prove it until one discovery changed modern physics forever. This is the story of the particle that decides why matter is solid, why stars burn, and why you are not just a cloud of light drifting through space. This is the story behind the so-called God particle, a name that sounds mythical, dramatic, and even controversial, yet hides a very real scientific truth. In this video, you will learn what the God particle truly is, why it took nearly half a century to find, and why its discovery shook the foundations of science. You will understand how an invisible field fills the entire universe, how it quietly gives mass to everything, and why without it nothing could ever form. No atoms, no planets, no life. You will also learn lesser-known details that rarely make headlines, like why some scientists resisted the idea for years, why others feared what would happen if it was never found, and why its discovery raised new questions that science still cannot answer today. This is not just a lesson in physics, it is a journey into the deepest layer of reality, where existence itself is decided. Stay with us until the end, because what seems like a simple particle leads to one of the biggest mysteries ever uncovered. Welcome to our channel. If you enjoy deep stories that explain the universe in a clear and powerful way, subscribe now and become part of this journey into the hidden rules of reality. The name God particle sounds powerful, dramatic, and almost mystical, but in reality it began as a nickname, not a scientific title. Scientists do not use this name in their work. The real name is the Higgs boson, and it is one of the most important particles ever proposed in physics. It is not powerful because it creates the universe or controls it. It is powerful because it explains why anything in the universe can exist as matter at all. The Higgs boson is a subatomic particle, meaning it is smaller than atoms, and even smaller than the particles inside atoms. It cannot be seen, touched, or directly observed in the normal sense. It appears only for a tiny moment and then disappears. What makes it special is not the particle alone, but what it represents. The Higgs boson is linked to something much bigger and far more important than itself, a field that fills the entire universe. This field is called the Higgs field, and it exists everywhere, even in the emptiest parts of space. It does not sit in one place. It does not turn on or off. It is always there. From the moment the universe began, this field has been present, shaping reality in silence. The Higgs boson is simply the visible sign that this field exists. It is the proof scientists were searching for. Without this field, particles would move at the speed of light and would have no mass at all. They would not stick together. They would not slow down. They would not form atoms. Without atoms, there would be no chemistry. Without chemistry, there would be no stars, no planets, no oceans, and no life. Everything solid depends on this field, even though no one can see it. To understand this idea, it helps to stop thinking of the universe as empty space with objects floating inside it. Instead, think of space itself as active, filled with invisible layers that affect how particles behave. The Higgs field is one of those layers. It is not made of matter. It is not energy in the usual sense. It is a background presence that interacts with particles as they move through it. Some particles interact with the field very strongly. When they do, they gain a lot of mass. Other particles interact weakly and gain only a small amount of mass. Some particles do not interact with the field at all. These particles remain massless and move at the speed of light. Light itself is made of particles called photons, and photons do not interact with the Higgs field. That is why light has no mass and can travel so fast. The Higgs field treats different particles in different ways, and this difference is what creates the variety of matter in the universe. It is not random. It follows strict rules. These rules are written into the structure of reality itself. A simple way to understand this is to think about movement. When something moves through empty space with no resistance, it moves freely and quickly. When it moves through a thick substance, it slows down. The Higgs field acts like that thick substance, but only for certain particles. Some particles move through it as if it is barely there. Others struggle as they pass through it and become heavier as a result. This slowing down is what we call mass. Mass is not just an object sitting still. It is a measure of how much a particle resists movement and change. The Higgs field gives particles this resistance. Without the field, everything would move like light. With the field, matter gains weight, structure, and stability. This is why the Higgs field is more important than the Higgs boson itself. The field does the work. The boson is just the messenger. For many years, the Higgs field was only an idea. It existed in equations, not in experiments. Scientists believed that if the field was real, there had to be a particle linked to it. That particle was the Higgs boson. Finding it would confirm the field existed. Not finding it would mean something was wrong with the theory. This created tension in the world of physics. Entire models of how the universe works depended on this one idea. The standard model of particle physics, which explains how particles and forces interact, required the Higgs field to function correctly. Without it, the model collapsed. Forces would not behave as predicted. Particles would not have the properties scientists measured in experiments. The Higgs boson became the missing piece, the final part of a puzzle that had been under construction for decades. The search for the Higgs boson was not simple. It required extreme conditions that do not exist naturally on Earth. The particle is very heavy compared to others at the subatomic level, and it decays almost instantly after it forms. This means it cannot be captured or stored. It must be created and detected in the same moment. To do this, scientists needed enormous machines capable of smashing particles together at incredible speeds. These collisions briefly recreated the conditions that existed just after the universe began. From this chaos, new particles could appear, including the Higgs boson, if it truly existed. The challenge was not only creating it, but identifying it among countless other particles produced in each collision. The signal was small. The noise was overwhelming. It took years of data collection, analysis, and verification to separate truth from coincidence. When the Higgs boson was finally detected in 2012, it was not a single moment of discovery, but the result of millions of events analyzed over time. Scientists observed patterns that matched the predictions made decades earlier. These patterns showed the presence of a new particle with the exact properties expected of the Higgs boson. This was not just a victory for one experiment or one group of scientists. It was a confirmation of an idea that had shaped modern physics for half a century. The discovery showed that the Higgs field is real and that it plays the role scientists believed it did. It explained why particles have mass without breaking the laws of physics. It showed that empty space is not truly empty. It is filled with structure and influence. The importance of the Higgs boson goes beyond its own existence. It connects directly to the question of why the universe looks the way it does. In the early universe, everything was extremely hot and dense. Particles moved freely and had no mass in the way we understand it today. As the universe cooled, the Higgs field changed. It settled into a stable state, and particles began interacting with it. This moment defined the structure of the universe. It allowed matter to slow down, clump together, and form complex systems. Without this transition, the universe would be unrecognizable. There would be no galaxies, no stars, and no planets. The Higgs field made complexity possible. Even now, the Higgs boson continues to raise questions. Scientists study how it interacts with other particles, how stable it is, and whether it behaves exactly as predicted. Small differences could point to new physics beyond the standard model. They could reveal hidden dimensions, unknown forces, or new types of particles. The Higgs boson is not the end of the story. It is a doorway. It confirms what scientists believe, but it also highlights what they do not yet understand. Why does the Higgs field have the strength it does? Why do particles interact with it in the specific way they do? Why does the universe allow mass at all instead of remaining a sea of light? These questions remain open. The God particle is not a creator or a ruler. It is a quiet mechanism, working everywhere at once, shaping reality without effort or awareness. It does not act with purpose. It follows rules, yet those rules allow everything else to exist. Every object, every structure, every living being depends on this invisible field and the particles linked to it. The Higgs boson matters because it proves that reality has depth beneath what we see. It shows that the universe is not just space and matter, but a complex system of hidden forces that work together to produce the world we know. And even though the Higgs boson itself appears only for a fraction of a second, its influence lasts forever, woven into the fabric of existence, shaping every moment without ever being seen. The name God particle creates a powerful image, but its origin is far less dramatic than many people assume. It was never meant to suggest divinity, creation, or religion. The term came from the title of a popular science book written to capture attention, not to define meaning. Inside the scientific community, the name has always been uncomfortable. Physicists prefer precision, and this nickname does not describe what the particle does or why it matters. The real name, Higgs boson, reflects its place in theory and its connection to the Higgs field. The nickname spread because it was memorable, mysterious, and easy to repeat. Media outlets embraced it, and the public followed. Over time, the name took on a life of its own, often leading to confusion. Some people believed the particle explained creation itself. Others thought it challenged belief systems. In reality, it does neither. It explains mass, not meaning. Scientists often stress that the name hides the true beauty of the discovery, which lies in mathematics, experimentation, and patience, rather than drama. The Higgs boson does not answer why the universe exists. It explains how matter behaves within it. That distinction is important, and it is one reason many researchers avoid the nickname entirely. The difficulty of finding the Higgs boson is one of the greatest challenges ever faced in experimental science. The particle is not just small, it is rare. It does not exist freely in nature today. It can only be created under extreme conditions, similar to those present shortly after the universe began. Even when it appears, it survives for an incredibly short time before breaking apart into other particles. Scientists cannot see it directly. They must infer its existence by studying what it decays into. This requires precise instruments, careful timing, and massive amounts of data. Millions of particle collisions can occur without producing a single Higgs boson. Even when one is produced, its signal can be buried under countless other events that look similar. Distinguishing a real signal from background noise takes years of analysis and independent confirmation. Small errors can lead to false discoveries. This is why scientists move slowly and demand strong evidence before making claims. To create the conditions needed to produce the Higgs boson, scientists built the Large Hadron Collider, the most powerful machine ever constructed for scientific research. It is buried deep underground and stretches for many kilometers. Inside it, particles are accelerated to near the speed of light and smashed together with enormous energy. These collisions briefly release enough energy to create heavy particles that do not normally exist. The Higgs boson is one of them. Building and operating this machine required international cooperation, advanced engineering, and decades of planning. Thousands of scientists and engineers worked together, each contributing a small part to a massive effort. The discovery of the Higgs boson was not a sudden surprise. It was the result of persistence, patience, and belief in an idea that could not be proven until technology caught up with theory. The impact of the Higgs boson reaches far beyond particle physics. Its discovery confirmed a key part of the Standard Model, the framework that describes how fundamental particles and forces interact. Without the Higgs field, this model could not explain why particles have mass, while still obeying the rules of quantum physics. Confirming the Higgs boson meant confirming that the model works as expected, at least within the limits tested so far. This gave scientists confidence in their understanding of the smallest building blocks of reality. At the same time, it highlighted the limits of that understanding. The Standard Model does not explain everything. It does not include gravity in a complete way. It does not explain dark matter or dark energy. It does not explain why the values of certain constants are what they are. The Higgs boson fits perfectly into the model, but it also draws attention to what lies beyond it. The technologies developed to find the Higgs boson have had wide-reaching effects. Handling the enormous amounts of data produced by particle collisions required new methods of data processing and analysis. This pushed advances in computing, networking, and data storage. Techniques developed for particle detectors have influenced medical imaging and other fields. Precision instruments designed to track particles have improved measurement technologies across science and industry. The search for the Higgs boson was not just about answering a question, it was about building tools and knowledge that could be used in many areas. The benefits spread quietly, often unnoticed, into everyday technology. The discovery also changed how scientists think about empty space. Space is no longer viewed as a passive backdrop where events happen. It is active, structured, and influential. The Higgs field is part of that structure. It shows that what appears empty can shape the behavior of everything within it. This idea has implications for how scientists approach other mysteries. If one invisible field can define mass, there may be others that influence forces we do not yet understand. This has encouraged new theories and experiments aimed at uncovering deeper layers of reality. Research into the Higgs boson did not stop after its discovery. Scientists continue to study its properties in detail. They measure how often it appears, how it decays, and how it interacts with other particles. Any deviation from predictions could signal new physics. Even small differences matter. They could point toward unknown particles or forces that exist beyond current theories. Some ideas suggest that the Higgs field could be connected to dark matter, the unseen substance that makes up much of the universe's mass. Others suggest it could play a role in understanding why the universe is stable instead of collapsing or tearing itself apart. The Higgs boson also raises questions about the early universe. Its field likely played a role in shaping the universe moments after the beginning. Studying it helps scientists reconstruct those early conditions. This connects particle physics with cosmology, linking the smallest scales with the largest structures. Galaxies, clusters, and the overall shape of the universe may all be influenced by processes connected to fields like the Higgs. This unity between the very small and the very large is one of the most striking features of modern physics. As experiments continue, scientists push for higher energies and more precise measurements. They look for rare events that could reveal cracks in existing theories. They explore whether the Higgs boson is truly alone or part of a larger family of particles. Some theories predict additional Higgs-like particles that have not yet been observed. Finding them would change the picture entirely. Even not finding them provides valuable information, narrowing the range of possible theories and guiding future research. The story of the God particle is still unfolding. Its name may be misleading, but its role is clear. It stands at the center of one of the most successful scientific frameworks ever created. At the same time, it acts as a reminder that knowledge is incomplete. Every answer opens new questions. Every discovery reveals new gaps. The Higgs boson confirms what scientists believed, yet it also invites them to look further, deeper, and more carefully into the structure of reality, where unseen forces continue to shape the universe in ways that are only beginning to be understood. Without the Higgs field and the Higgs boson, the universe would not look the way it does today. Matter would never slow down, particles would never gain weight, atoms would never form, stars would never ignite, planets would never take shape, life would never begin. Everything familiar would simply fail to exist. What makes this idea so powerful is that nothing about it is mystical or symbolic. There is no hidden meaning or supernatural force at work. It is physics, precise and silent, operating everywhere at once. An invisible field fills all of space, shaping reality without being seen, touched, or felt, yet defining every solid thing that has ever existed. The Higgs boson was not the creator of the universe, but the proof that this hidden structure is real. It showed that empty space is not empty at all. It is active, influential, and essential. The deeper scientists look, the clearer it becomes that reality is built on rules far more subtle than appearance suggests. And this discovery is not the end. It is a foundation for the next questions, the next theories, and the next breakthroughs that may one day explain even more about why the universe is the way it is. If you enjoyed this journey into one of the deepest secrets of reality, support the channel by liking the video, sharing it with others who love exploring the universe, and subscribing for more stories that reveal how the hidden laws of physics shape everything around us.